We have seen how to use the notions of positive semi-definite operators or transformations or matrices to find the right basis for our 4 subspaces. Let us recall some of these aspects. So, we first look at a matrix A, which is an m by n matrix real. Then connected with that we defined 2 square matrices, one L equal to A transpose A, which is an n by n square matrix, and M which is A transpose, which is an m by m square matrix. Both are real symmetric positive semi-definite matrices. This we saw last time. So, we define connected or associated with a given m by n matrix, m by n real matrix, 2 positive semi-definite real matrices. One was n by n, the other one was m by m. And we found that when we look at the decomposition of R n and R m are as follows. If we look at the R n side and the R m side, and we have A going this way and A transpose going this way, and R n, the fundamental decomposition corresponding to the matrix A was the 2 orthogonal spaces, null space of A and the range of A transpose. We found that the null space of A is the same as null space of the matrix square positive semi-definite matrix L, and the range of A transpose was the same as range of L. On the other side, we found that the fundamental decomposition with respect to the matrix was null space of A transpose and the range of A, and we found that the null space of A transpose is the same as null space of M, and the range of A was the same as range of M. Now, therefore, we found that all these 4 subspaces can be thought of as subspaces connected not just with a rectangular matrix, but with positive semi-definite matrices. So, using this idea, we found that the rank of all these matrices are connected. The rank of A is the same as rank of A transpose, is the same of the rank of L, is the same of rank of M. So, we denote now from now on rank by rho. So, since all these are equal, we denote by rho. The nullities were related as the nullity of A is the same as nullity of L, because the null space of A is the same as null space of L, and the nullity of A transpose is the same as nullity of M, because the null space of A transpose is the same as null space of M. Now, using these ideas, we found that we can find a basis phi 1, phi 2, phi nu A, which is an orthonormal basis for this null space of A as the orthonormal eigenvectors corresponding to the eigenvalue 0 of L. So, the basis that we found, that we said we could find, were 1 phi 1, phi 2, phi nu A, orthonormal basis for the null space of A. These are orthonormal eigenvectors corresponding to the eigenvalue 0 of the matrix L. Now, notice that if nu A is 0, then the 0 will not be an eigenvalue of L, and the null space of A will consist only of 0 vector, and we have to only focus on range of A transpose. Then we could find psi 1, psi 2, psi nu A transpose, an orthonormal basis for the null space of A transpose, and these are orthonormal eigenvectors corresponding to the eigenvalue 0 of the matrix M. So, that gives rise to these two bases, the two null spaces on either side. Then we went about the task of finding the basis for the other two subspaces. Then we found that V 1, V 2, V rho orthonormal basis for the range of A transpose. These are the orthonormal eigenvectors corresponding to the positive eigenvalues, which we arranged as eigenvalues of L arranged as lambda 1 greater than or equal to lambda 2 greater than or equal to lambda rho greater than 0. So, we found the basis for the range of A now. Now, using this basis we generated the basis for the range of A. How did we get that basis? If you recall, we define U 1, U 2, U rho orthonormal basis for range of A, where U j is defined as 1 by S j A V j for j equal to 1 to rho. S j is square root of lambda j, and these are called the singular values of A. And we had the fundamental relation that A V j was S j U j and A transpose U j was S j V j 1 less than or equal to j less than. So, our choice of basis, the way we selected the u's from the v's, make it that the A V j and A transpose U j are related this way. So, our choice of basis is very particular. For the range of A, A transpose, we pick the eigenvectors, the orthonormal eigenvectors corresponding to the positive eigenvalues of L, and from that we generate the basis U 1, U 2, U rho for the range of A transpose, and this way of choosing the basis makes this relationship between the basis for range of A transpose and the range of A connected such that the V j basis for range of A transpose goes to the direction of the U j basis of range of A with a multiplying or a scaling factor of S j, and the U j basis of the range of A goes to the V j direction of the range of A transpose with a same scaling factor as before S j. So, these are the facts that we observed in the last lecture. Now, we shall see how we use this, how do we use these facts. How do we use these facts to analyze the various questions about A and the structure of A. So, we would like to look at the general structure of an M by N matrix, and we want to look at the answers to the various questions that we raised about the matrix A. So, to this end we shall now begin our analysis using these facts of a general matrix. The first you may recall that we showed that if we have a Hermitian matrix, we could decompose this as a product of 3 matrices, the 2 extreme ones being unitary matrices. In the case of real, they were orthogonal matrices and the middle one was diagonal. So, recall if A is a Hermitian matrix, there exists. So, since we are dealing with real matrices at the moment, let us say A is real symmetric matrices. So, R n A belongs to R n n. So, if A is a real symmetric matrix, then there exists unitary in the case of real it will be orthogonal again. Let us restrict ourselves to the real case, real orthogonal matrix U belonging to R n n such that we could write A as the product of U and a diagonal matrix and U transpose where U is where D is diagonal. This was the result we had for a real symmetric matrix. Now, what we will do is we will look at a general version of this result for a general m by n matrix. So, now suppose A is a general m by n matrix and then we pick the orthonormal bases as above. That is, we construct the matrix L and then we pick up the phi 1, phi 2, phi nu A, psi 1, psi 2, psi nu A to transpose V 1, V 2, V rho, U 1, U 2, U rho as mentioned starting from the matrix L and M. So, we pick the orthonormal basis as above, then we construct the matrix U whose columns are the U vectors U 1, U 2, U rho, that is these are the orthonormal basis for the range of A, and then the remaining basis coming from the null space of A transpose. So, U is a matrix whose columns are formed by, if you look at this picture, whose columns are formed by this U 1, U 2, U rho and psi 1, psi 2. So, this together all these form a basis, each one of them is an m component vector, we have m of them, and what we do is we put them all together and we have this matrix U whose columns are these U 1, U 2, U rho. So, this is a matrix which is an m by m matrix, and now this is an orthogonal matrix because the columns are orthonormal vectors. Whenever you have a real matrix with columns orthonormal, it becomes an orthogonal matrix. Whenever you have a complex matrix whose columns are complex orthonormal, then it becomes a unitary matrix. What does it mean to say it is an orthogonal matrix? U transpose U is the identity matrix, which is the same as U U transpose, which means U transpose is U inverse and U transpose inverse is U. Analogously, similarly, if we define V, now we constructed the U matrix taking care of the basis on the R m side. Now, we construct the matrix V taking care of the basis on the R n side, that is V 1, V 2, V rho, phi 1, phi 2, phi nu A. Now, all these vectors in R n, there are n of them. So, this becomes an n by n matrix, and this is also orthogonal matrix. Now, it is an orthogonal n by n matrix since columns are orthonormal. Columns are orthonormal vectors, and therefore, V transpose V equal to identity. Now, n by n matrix, all are n by n matrices, V transpose, and V transpose inverse is V and V transpose is V inverse. So, these are two important matrices that we have constructed. Now, we look at A V. This is the same as A, V is this matrix phi 1, phi 2, phi nu A. Now, if you multiply, you get A V 1, the first column is A V 1, second column is A V 2, row column is A V rho, then we get A phi 1, A phi nu A. This is the same as A V 1, we knew from our choice of basis A V 1 is S 1 U 1, A V 2. If you look here, we have A V j is S j U j. So, A V 1 will be S 1 U 1, A V 2 will be S 2 U 2 and so on. We use that fact, and therefore, we can write this as S 1 U 1, then S 2 U 2, S rho U rho. Then phi 1 is in the null space of A. So, A phi 1 will be theta m, A phi 2 will be theta m, all these will be theta m, 0 columns, because phi 1, phi 2, phi nu A are all in the null space of A. So, A V is simply S 1 U 1, S 2 U 2, S rho U rho, and the last n minus rho columns are all 0. Now, let us multiply this matrix by U transpose. U transpose is U 1 transpose, U 2 transpose, U rho transpose, psi 1 transpose and psi nu A transpose transpose. That is U transpose into S 1 U 1, S 2 U 2, S rho U rho, theta m, etcetera theta m. Now, if you multiply, what do we get? First is U 1 transpose, we get U 1 transpose into U 1. U 1 transpose U 1 is 1, because these vectors are of length 1, all are orthonormal vectors. So, they are all of length 1. So, U 1 transpose U 1 is 1. So, I will just get S 1. So, the first entry is S 1. Next we have U 1 transpose U 2. Since U 1 and U 2 are orthogonal to each other, U 1 transpose U 2 will be 0. So, next one will be 0, and similarly U 1 transpose U rho will be 0. So, all the remainings are 0. Then we will get U 1 transpose the 0 vector, U 1 transpose the 0 vector and so on. So, all the remaining things will be 0. So, the first row will have only the leading entry as S 1 and all others are 0. Similarly, the second row has 0 S 2 0 0. It goes on up to the say row. Then beyond the row we have psi 1 transpose U 1, which is 0, psi 1 transpose U 2, that is 0, because they are orthogonal, psi 1 transpose U rho, that is 0, and psi 1 transpose the 0 vector, it is 0. So, all others are 0, all the other entries are 0 0 0, 0 0 0 and so on. So, we get a matrix like this, and let us see what it means. It means it has a nice diagonal block which has S 1, S 2, S rho on it, and all the others are 0. So, we will write it in this form, it in block form, a matrix S row by row, all the others are 0. So, this will be the 0 matrix with row columns and n minus rows and n minus row columns. This will be the 0 matrix. We have already taken rows here. So, the remaining m minus rows into row, and this will be 0 m minus row into n minus row. So, basically where S row is the diagonal matrix, S 1 the diagonal entries are the singular values. We will call this matrix as S A. So, S A is essentially a diagonal matrix, essentially a diagonal matrix. Only significant part, the non-zero part is a diagonal block, it is the leading diagonal block, and the diagonal entries are all the singular values of A. So, therefore, we have U transpose A V is equal to S A, or A equal to E transpose inverse is U, and V, if we take the other side, V inverse is V transpose, because these U and V are orthogonal matrices. The inverse of U is U transpose, the inverse of U transpose is U inverse, the inverse of V is V transpose. So, thus we see that A has been factorized into 3 factors. The 2 extreme factors are orthogonal matrices, and the middle one is essentially a diagonal matrix. Thus, we have a factorization of A into 3 factors. The 2 extreme factors are orthogonal matrices and the middle one is essentially a diagonal matrix. When we say essentially a diagonal matrix, what we mean is that the only significant part of the matrix is a leading diagonal block consisting of the singular values along the diagonal and all other entries being 0. Note that in the 2 extreme factors, the U is an m by m factor matrix and this V transpose is an n by n, and this the middle one S A is an m by n matrix. So, that the product is again m by n. This is called the singular value decomposition of A. We will generally denote it by SVD of A. SVD means singular value decomposition, and in the case of Hermitian matrices, since everything in the square, the extreme matrices can be chosen to be the same, and that is what we got in the you got U diagonal U transpose. In the case when m equal to n, in case we have m equal to n. So, let us say we have a square matrix, we get A equal to U, which is now an n by n orthogonal matrix, S A, which is now an n by n matrix because m equal to n, V transpose, which is again an n by n orthogonal matrix. Now, how does S A look like? We get the SVD as the singular value decomposition. S A is now an n by n matrix. It has S 1, S 2, S row along the diagonals and all the others are 0, 0 n minus row I am sorry, this is remaining number of rows is n minus row, columns is row. Here is remaining columns is n minus row, here is n minus row, n minus row, which simply means it is the diagonal matrix S1, S2, S row, and all the other entries are 0. So, therefore, we see a general version of the diagonalization theorem. If we have any matrix A, any real matrix A which is square. So, if you have any real square matrix A, it can be always written as the product of 3 matrices, the extreme 2 being orthogonal n by n matrices and the middle one being a diagonal matrix. Okay. So, thus we have a general diagonalization theorem for any n by n real matrix. Recall that when we talked of diagonalization of the form P inverse A P should be diagonal, we always required that algebraic multiplicity of the eigenvalue to be equal to the geometric multiplicity of the eigenvalue, and we found examples where this was not valid, and therefore, there were matrices which were not diagonalizable in that format. But now we see that if you allow the 2 extreme factors to be 2 different orthogonal matrices, then we are always able to diagonalize a matrix. So, we have this general diagonalization theorem for any n by n matrix. So, given A belonging to R n cross n, there exists unitary, now since we are in the real case, I should write orthogonal matrices, there exists orthogonal matrices U V in n by n such that U A equal to U D V transpose, where D is a diagonal matrix in R cross n. So, this the diagonal entries are now not connected with the eigenvalues, but they are connected with the singular values. So, where D equal to the diagonal matrix S1, S2, S row 0, 0, 0, 0, S1, S2, S row, the singular values of A. And of course, row is the rank of A. If row is n, it is S1, S2, Sn, a full diagonal matrix. So, thus we have this generalization of the idea of the factorization we had for Hermitian matrices, we have the generalization of the idea of diagonalization we had for matrices with algebraic multiplicity equal to geometric multiplicity for all eigenvalues. So, this is a generalization of one, the factorization we had for Hermitian matrices, and 2, the diagonalization we had for matrices which were diagonalizable over Cn. So, these are the here in the case of this sort of general diagonalization, we do not have to resort to complex polynomials etc. We are always guaranteed that all these can be done over the reals. So, if you want to restrict over reals, then any matrix A can be diagonalized in this format, namely U D V transpose, where D is diagonal and U and V are orthogonal matrix. And also if you take any general matrix, m by n matrix, non-square, even rectangular matrix, then A can be factorized into this form, the so called SVD. In the case, in the general case, the SVD involves m by n matrices. The in general A belonging to Rmn can be factored as U SA V transpose, where U and V are orthogonal and SA is essentially diagonal. So, thus we have the factorization theorems and the diagonalization theorem, all of them coming out as a consequence of our basis that we chose. This worked out well because our U and V that we chose were well behaved. However, the U's and V's coming from, U's were coming from the basis for Rm that we chose, and the matrix V was coming from the basis we chose for Rn. So, it is this right choice of basis that we made that made things work and gave us the factorization of the matrix A. So, that is the first consequence, this generalization of these factorization ideas and the generalization of these diagonalization ideas are the first consequences of the type of basis that we have chosen in studying the structure of the matrix A. Now, let us look at the same thing in a different context, in a different viewpoint. Remember, we also studied that when we had Hermitian matrices, on the one hand we had the factorization of the matrix into 3 parts: unitary, diagonal, unitary. Also on the other hand, we said that a Hermitian matrix of rank rho can be decomposed as the sum of row 1 rank matrices. Analogously, we shall now see that if we take any general rectangular matrix also, or any square matrix, or any matrix, real matrix for that matter, and this could be extended to complex matrices. So, if we take any matrix A belonging to R m cross n, m may be equal to n, m may not be equal to n, m may be greater than n, m may be less than n, it is irrelevant. If we give any matrix A belonging to R m n, if its rank is rho, we shall see that it can be written as the sum of row 1 rank matrices. This is the sum decomposition, and this will be the some version of the singular value decomposition. We have obtained above the singular value decomposition in the product form. Now, we will get the singular value decomposition in the sum form. So, let us now start with any matrix R m cross n, and again we have the basis as above. The moment a matrix is given, we will construct the L and M, and we will choose the basis for R n and R m as explained above, the U 1 U 2 U rho, phi 1 phi 2 phi nu A for the R n side, and the U 1 U V 1 V 2 V rho and the phi 1 phi 2 phi nu A for the R n side, U 1 U 2 U rho and the psi 1s on the other side. So, we have the above basis. What is the consequence of the basis in terms of this sum? Now, we have V 1, V 2, V rho, phi 1, phi 2, phi nu A is an orthonormal basis for R n. The moment we have an orthonormal basis for a vector space, we can always expand any vector in terms of this orthonormal basis. Therefore, x belongs to R n implies x can be expanded in terms of this orthonormal basis. What is this expansion? That is, x is equal to, we have to take the components along the v directions and the components along the phi direction. So, we will write it as j equal to 1 to rho x comma vj vj. These are the components along the vj direction x vj times the vector, the base vector, and then we will write r equal to 1 to nu a, the components along the phi directions. This is the so called Fourier expansion in terms of the orthonormal basis. We have seen that the moment we have an orthonormal basis, we always have a Fourier expansion of this form. Now, once we have this, what does that say about A x? Now, A x can be matrix multiplication is distributive over the sum. So, we can take the product sum term by term. X v j is a number because it is the component times A v j plus summation r equal to 1 to nu a, x phi r is a number times A phi r. That says j equal to 1 to rho. Remember that according to our choice of the basis, A v j was S j u j. That is how we chose the basis. The way we have chosen the basis forced A v j to be S j u j. The v j direction went to the u j direction with the scaling factor S j plus r equal to 1 to nu a. What is A phi r? Phi r's are all in the null space of A. So, A phi r is the 0 vector. So, all these terms just give the 0 vector. So, we can ignore them because A phi r is equal to theta m for 1 less than or equal to r less than or equal to nu a, and A v j is equal to S j u j. These two facts we know by the choice of our basis. So, we have A x equal to S. So, thus x belongs to R n implies A x equal to summation j equal to 1 to rho x v j S j u j. This, well, let us call this as equation 1. Now, let us put this equation 1 in a different form. First of all, we observe that x v j, we are all in the real case. So, the x v j, the inner product between x and v j is just v j transpose x. Okay. It is the inner product in the real case is v j transpose x, in the complex case it is v j star x. So, since we are dealing with real vectors, x comma v j is v j transpose, and therefore, x comma v j S j u j is the same as S j v j transpose x into u j. Now, for any u in R m and v in R n, we define the tensor product v tensor or v cross u as u v transpose. Now, since v is in R m, this is m by 1, v is in n. So, this will be 1 by n. So, this will be an m by n matrix in R m n. So, it is real. So, if u is in R m, v is in R n, v tensor u defined as v tensor u is equal to u v transpose is an m by n matrix. And now, if we take x in R n, v tensor u, this is a matrix multiplying x. So, this is an m by n matrix, this is an n by n vector. I should get an m by 1 vector by v tensor u is u v transpose x. So, this is nothing but v transpose which now matrix multiplication is associative. I can write it as u v transpose x. V transpose x, v is in R n, x is in R n, v transpose x is a number. So, we can write this as v transpose x times the vector u. So, for any x in R n, v tensor u x is equal to v transpose x into u. If we use that notation, we will see that V transpose x into uj can be written as Vj transpose Vj tensor uj acting on x. Therefore, Vj tensor uj acting on x is Vj transpose x uj. So, therefore, we can now write Sj times Vj transpose x times uj as Sj into Vj tensor uj acting on x. So, let us now substitute this in 1. So, therefore, 1 can be written as x belongs to Rn implies Ax equal to summation j equal to 1 to rho. We have 1 here Sj and xvj is, as we observed, Vj transpose x, and combining that we get Vj tensor uj. So, in other words, it is the action of x on a number of matrices. We can write this as summation j equal to 1 to rho Sj Vj tensor uj, this whole thing is acting on x. Each term in the sum is an m by n matrix, because the tensor product of Vj and uj, Vj is in Rn, uj is in Rm. By our definition, this is an m by n matrix. So, we have a sum of m by n matrices. So, this is an m by n matrix, let us call it as K. This K belongs to m by n. So, therefore, x belongs to Rn implies Ax equal to Kx. Now, if two matrices coincide at all the vectors, if Ax equal to Kx for all the x, then A must be equal to K. So, that says A equal to summation j equal to 1 to rho Sj Vj uj, and each term is a matrix of rank 1, because as you see here in the tensor product, if you, when you take the tensor product, the range is consists of any vector of this form, and it is always a multiple of the vector u, constant times u. So, u spans the range. So, therefore, if you take this Vj tensor uj, uj will span the range, therefore, the rank is 1. So, each one of the matrices in the sum is rank 1, and therefore, we have a sum of row 1 rank matrices. Okay. So, each term in the sum is an m by n matrix of rank 1. So, thus we have A is any A belonging to R m cross n of rank rho can be expressed as the sum of row 1 ranked m by n matrices. So, thus we have the sum decomposition of a row rank matrix. This decomposition that we have called, this will be called the SVD, the sum version. We saw the product version of the decomposition into 3 matrices, product of 3 matrices. Now, we have the sum decomposition of any m by n real matrix. We have the sum decomposition. If the rank of the matrix is row, then we can decompose it into row matrices each of rank 1. So, this is the generalization of such a decomposition we had for a Hermitian matrix. So, for a Hermitian matrix we had product decomposition, analogous to that for a general m by n matrix we have product decomposition. For a Hermitian matrix we had a sum decomposition, analogous to that we have for any general m by n matrix we have sum decomposition. For a Hermitian matrix we had a diagonal decomposition, corresponding to that for a general m by n matrix we have essentially diagonal decomposition. All these are related to the SVD of the matrix. So, let us write down the summary of all our discussions so far. So, the summary is A belongs to m by n matrix. We will repeat the whole structure. We define L to be A transpose A. This belongs to R n n, symmetric. So, it is real symmetric n by n matrix. M to be A transpose, it is an m by m matrix and symmetric, and both are positive semi definite. These yield us the following bases, which are orthonormal. Again we will write the picture that we had. This is R n, and this is R m. A is a mapping from here to there and A transpose on this side, and this is the range of A transpose, which was the range of L. This is the null space of A, which was equal to null space of L. This is the range of A, which was equal to range of M, and this was the null space of A transpose, which was equal to the null space of M. We found orthonormal bases for this, which were coming from the eigenvectors corresponding to the 0 eigenvalue of the matrix L, and we found the beds orthonormal basis V 1, V 2, 0. These were the orthonormal eigenvectors coming from the positive eigenvalues of L arranged in the form lambda 1 greater than or equal to lambda 2 greater than or equal to lambda rho greater than 0. Then we got the basis here, and these came from the orthonormal eigenvectors corresponding to the eigenvalue 0 of the matrix M. Then we got the basis here u 1 u 2 u rho with u j defined as 1 by S j A V j 1 less than or equal to j less than or equal to rho, where S j is the square root of lambda j, the lambda j being the jth positive square root of positive eigenvalue of L. Remember, we arrange them as lambda 1 greater than or equal to lambda 2 greater than or equal to lambda rho and the jth one, and these are called the singular values of the matrix. So, these are called singular values of A, and then we had the relation that A V j is S j U j, this is from the definition itself, and similarly A transpose U j is S j B j. Then we defined V to be the matrix whose columns are V 1, V 2, V rho, phi 1, phi 2, phi nu A, U to be the matrix U 1, U 2, U rho, psi 1, psi 2, psi nu A transpose. This was an n by n matrix, this was an m by m matrix, and this was orthogonal n by n matrix, that is V transpose V is identity, this was orthogonal m by m matrix. So, orthogonal here means V transpose is V inverse, V equal to V transpose inverse, and V transpose V is identity. Similarly, U transpose U is identity and each is the inverse of the other. We had these two orthogonal matrices, then we had this product decomposition. The product decomposition is of A is A equal to U S A V transpose, where S A was in block form S row by row matrix, a diagonal block. The rest of them are 0. This is 0, m minus row, n minus row. This is 0, I am sorry, this is 0, m minus row row, and this is 0, m minus row, n minus row. So, this was in diagonal block, and S row row was the diagonal matrix whose diagonal entries were S row, S 1, S 2, S row, the singular values of the matrix here. So, the first thing that we had was the product decomposition, then we had the sum decomposition. These are the SVDs. When we say decomposition, we mean the singular value. Since the diagonal entries are in singular values here, we call it the singular So, this is the product decomposition, the product version of the SVD, and then we had the sum decomposition. A is equal to summation j equal to 1 to rho S j V j tensor U j, where V j tensor U j, our notation is U j V j transpose. So, these are the two main decompositions that we get. So, from the basis, from the choice of our basis, we are able to get the generalization of the product decomposition we had for the symmetric or the Hermitian matrices. We are also able to get the sum decomposition that we had for Hermitian matrices. Now, how do we use these bases we have chosen to analyze the system of equations A x equal to b? Remember, we are given A is in R m cross n and B in R m. We want to find x in R n such that A x equal to b. This is our problem of the system of equation. Now, we are going to use the basis that we have chosen in order to analyze the system of equations. So, remember what are the questions that we asked? The questions that we have to answer is, what is the consistency condition? The consistency condition, that is, what condition should be satisfy in order that the system has a solution. Then when B satisfies these conditions, we want to know how many solutions, then if it is unique, we want to find the solution. If infinite, the number of solutions is infinite, find all and find unique representative solution. Among the many solutions that we have, we must say what is some criterion that we can use in order to pick a representative solution. And then we have to worry about when B does not satisfy these conditions, then we have to worry about what is known as the least square solutions. Then we have to worry about uniqueness or infinite, and if it is unique, we want to find the unique solution, and if it is infinite, find all and find the unique representative. Now, these are the fundamental questions that we raised about a system of equations. Consistency condition, if it is satisfied, solution exists, unique, find it, infinite, find all and find a representative. If it does not satisfy, then you can do what is meant by least square solutions. Then is it unique, is it infinite? If it is unique, find it. If it is infinite, then find all of them, and among them how do we choose a core solution or a representative solution. These are all the fundamental questions. Now, we shall see how to use the basis that we have chosen in order to analyze all these questions and get satisfactory answers. This will be our next topic.